Yeah.
All right, cool. Okay, so welcome everyone to our second to last class. Today we're going to be jumping into something super exciting and honestly the best part of this course, which is called neural networks. Now, if you're into research or, if you think of where AI is used, most often it's going to be used with a neural network as opposed to the other algorithms that we've learned before. So previously we went over linear regression and logistic regression. Well, those models are typically used as baselines or like testing before people actually incorporate neural networks, which are a lot more complex and a lot more accurate than those. So these are a lot smarter, and we'll go into exactly how they work in this lesson, and we're super excited to teach you guys. So, quick class overview. We're going to start with obviously neural network theory, basically how it works. We're going to go ahead and code a neural network or design a neural network. We're going to do some announcement. And finally, we have team applications out. So, we're going to be sending team applications out and we're going to give you more information about the roles. So, if you guys are interested, please stay till the end of class to hear about that. And I think it's a great opportunity that you guys should not be missing out on. So with that, let's just get started. All right. First, we have neural network theory. So starting with what are neural networks? Now, I'm going to give you this broad level definition here. Don't worry if you don't understand it just yet. We're going to dissect it and go into it more deeper in the next couple of slides. But basically, what a neural network is a system of connected neurons that learn patterns from data to make decisions or predictions. What you should be taking out of this slide is that neural networks are heavily inspired by the brain, and we'll go into exactly how right now. So, you're probably wondering, what is a neuron, or more specifically, an artificial neuron? So, well, to understand what that is, we first have to start by understanding what they're modeled after. So, artificial neurons are inspired by everyone's favorite biology. So, if you've taken any biology class before, you're probably familiar with what neurons are. And if you're not familiar, don't worry, we're about to go over it right now. So, neurons in biology are cells that help us interpret signals, or cells that help us as humans basically interact with the world. They're the building blocks of our brain and our nervous system. So, as their input, they get signals from other cells. They process these inputs or signals and they get excited at certain signals and they start charging electricity. And if the electricity that they charge reaches above a certain point, then that signal will be transferred and outputted through the neuron and it'll get sent to other cells. So, to better understand that, let's look at an example. So let's look at touching a hot stuff. So when you go near, let's say you're cooking and you accidentally touch a hot stuff, what do you do? Well, you're probably gonna pull your hand back, right? Now, the reason that happens is because signals, when you touch the stuff, were sent to your brain or to your neurons in the brain, and they were received at these points right here. So these points right here called dendrites, those signals were received into that cell. So this picture is a model of what a neuron is. So when those signals were received, they were processed in the cell body. So this place right here. And by processed, I mean that the cell basically understood what the signal is. And after understanding the signal, the cell then decides, is it important or is it not important? Like, should I react to it or should I not react to it? And so after processing it, if it decides to react to it, an electrical signal will be sent through this chain right here and will be outputted through this axon terminal. So don't worry about these biological terms. I'm just showing you what this image is referring to. But this is what a neuron in biology is. It's basically a cell that helps us process information. So going back to our hot stove example, so once that signal of heat or like pain was received by this cell, it was it was processed through the cell body, and then an electric signal was sent out to other cells to tell you to move your hand back. So basically, neurons are basically communicators. They help us communicate. Now, that's what neurons are in biology. But what about neurons in artificial? in math. Hold on, let me clear my annotations. So, when it comes to neural networks, we're obviously not using cells, right? We're not using cells from our brain to make AI models. So, what exactly are artificial neurons, which are the neurons we use in neural networks? Well, artificial neurons are basically duplicates of biological neurons, but in math. So that same behavior we talked about, the same one right here of the inputting, the processing, the outputting with biological neurons happens with these artificial neurons in math as well. So let's explore exactly how that works. So, starting with the input. So artificial neurons take in numerical input just like how neurons take in signals as input. So if you go back, recall that in those dendrites, these little branchy things at the start of the cell, those places receive input. Well, similarly, artificial neurons also take in input. So to look at that, we have a big panel of inputs right here. You know, input is typically denoted by x. So here we have x1, x2, x3, and so on and so forth up to x of n. So this basically just represents a chain of inputs, basically many different kinds of inputs. Next, inputs in these artificial neurons in math are multiplied by things called weights. Now, if you were here for our last lessons, you know that weights basically tell the model how important a certain input is. And when these inputs are multiplied by weights, they're essentially getting processed. And these artificial neurons will get more excited about certain inputs, like how neurons get more excited from certain signals. So think about it for a second logically, right? If a certain input is multiplied by a bigger weight, so let's say I have an input of 5, right? And my weight is going to be 3, and then I have an input of 4 and the weight for that is going to be 2, which one's going to be bigger? Obviously the 5, right? The 5 multiplied by the 3 weight. That's 15 and it's bigger than the other number. So when the artificial neuron looks at this, it gets more excited in a way, like excited. That means that it looks at it and makes it more important. It deems it more important because it's been multiplied by a bigger weight. So those are our weights right here. So we're taking our inputs, we're multiplying them by weights. Now the next step is obviously our processing. So these inputs are going to be processed by summing up all of the weighted values for each input through something called a transfer function. Now know I just threw a lot of words at you, but trust me, it'll make sense in a minute. So basically, one of our artificial neurons is getting a lot of inputs, right? You can see that we're having a lot of inputs here. And those inputs are being multiplied by weights. So now they're getting multiplied by number, and now they're bigger, right? What a transfer function does is it just adds the sum of all of those inputs after being multiplied by weights. So to look at that, this is a representation of that function. It's denoted by z, and you can see x1 times weight 1 is added to x2 times weight 2, and so on and so forth. So I know it looks like a lot of mathematical notation, but in reality, all that's happening is we're finding the sum of all of our inputs that have been multiplied by their respective weights. So in our image, it looks like this. So to take a minute to pause, we've taken our inputs, we've multiplied by weights, which lets the model know how important a certain input is towards making a prediction. And we've taken the sum of all of those inputs after they've been multiplied by weights. So if you guys have taken like pre-calculus or algebra, you probably are familiar with this symbol, which is summation, which basically tells you that you're getting the sum of everything before it. So that's what this transfer function is doing. Now the next step is something called an activation function. Now, this is super, super important to understand in neural networks and beyond, because these activation functions are what are the things that allow these neural networks to detect these complex patterns. And we have a whole slide on that a little bit later. But the point is, these inputs are then passed through an activation function to decide whether or not to send the input forward and how strongly. So if you recall, with our neurons, we saw them getting fired up or producing an electric charge at certain signals, right? The thing is, it doesn't do that with every single signal it gets. If it gets some like small signal, like your body is always detecting signals all the time, right? You're touching things, you're doing things, but your neurons don't need to be responding to every single little signal that your body is detecting. That's why your model or your neurons in your brain essentially gauge which signals are important and react to those first. In this case, artificial neurons are doing the same thing. So after taking into account the weights and the inputs, is getting passed through an activation function, which helps the neuron, in this case, decide whether or not to send the input forward into the next neuron. So looking at how that looks like, after finding the summation, we take that summation and put it into something called an activation function, which basically determines if that input is going to be moved forward in the model or not. So if you look here at this diagram, we see the transfer function. Whatever the output of that transfer function is, we're seeing it getting fed into the activation function, which then gauges whether or not to send that forward as the activation value. Now, we have a whole slide on this coming up, so don't worry if you don't understand exactly what activation functions are or if you have questions. Ask us after that slide is done. So this is basically a general structure of a singular neuron. Now, neural networks are not made of just one neuron, but they're made of many, and you'll see how that like entire architecture looks in just a minute. And let me tell you that architecture looks really, really cool. I think you guys are going to be pretty shocked to see what it looks like. But this is what one neuron is doing in a neural network. As a recap, it's taking input, multiplying by weights, putting it through a transfer function to find the sum of all of those weighted inputs, and then that sum is being passed through an activation function to determine whether or not those inputs get fed over to the next model, because not every input is important. So that's what our activation function understands. Now, I'm going to throw it over to Aveen, who's going to discuss what these activation functions actually do.
Okay, yeah. So just like Darshi was just saying, what each of these neurons is doing, like just like she just broke it down, it's deciding whether or not to pass like a signal forward. But like, how does it make the decision whether to pass that signal forward or not? Like that is what the activation function is doing. That's when the activation function comes in. So basically, it's allowing the network to like learn complex patterns because without them, the network would only be able to do like simple linear operations. You could honestly think of the activation function like a filter that's shaping the original signal so the network can understand these complex, complicated relationships. You can see like on this little diagram on the right side, we have a couple of different examples of activation functions. We have tanh, ReLU, sigmoid, and linear. There's a couple other examples too, but the two functions that we're going to be covering today, because it's important to our project, is ReLU and softmax. So ReLU basically, it just passes positive values as they are, but it turns negative values into zero. This is really helpful because it makes it a lot more simple and it avoids messy math and it just helps the network learn faster. Like if we look at the graph, we can see here that any of the negative values on the left side of the y-axis, it's all flat, it's all zero. But then if you look at the right side, all of those positive values, it's all going up. And then the other function that we're going to be using is softmax. Basically what it does, it just turns a set of numbers into probabilities that adds up to 100%. It's really helpful for classification problems because it just tells you like which option is most likely. Okay, and now so far, like just like Darshi was explaining, she broke it down. We've understood what is inside neural networks. We've understood the artificial neurons. Now we just need to understand like how they work together to form these actual neural networks. So yeah, just going back to what like that she like really detailed and she like broke down. Each neuron is like receiving information. It's doing a calculation and it's passing it on. You could think of it like a small function in Python that's like taking an input and it's multiplying it by the way, it's adding the bias and then applying the activation function. So if you look at this diagram, we have like each of these circles, it's essentially representing a neuron. So like all of that stuff that she talked about, it's happening within each of these circles. And then Each of these circles, we have four different columns. So each of these columns is what the layer is. So our first layer we have is an input layer. So each like neuron is representing one feature of your data. For example, in Python, like if your data has like 10 features, then you're gonna have an input layer of 10 neurons. Then if we look all the way at the end of the diagram, we have an output layer. This layer is producing the final answer. It could be like predicting a number, classifying an image, deciding like yes or no. So this is like at the beginning and at the end, but I'm sure you guys can see in between, we have these things called hidden layers. So these are the middle layers. We're not necessarily seeing their output like directly, but what they're doing is they're like discovering patterns and relationships. For example, like your code may have a hidden layer with 16 neurons. Each of these neurons is learning different combinations of the previously inputted features. And then when it comes to each of these layers too, the output from the previous layer is automatically becoming like the input to the next layer. And just because we're not directly seeing an output of each of these hidden layers, it's getting passed on like to the output layer. And like when it comes to like how you're gonna structure your own model too, depending on how you want to do it, you could have like fewer or more hidden layers. But we'll discuss more like about how many you want to have. We're gonna discuss that in a later slide. Now, how do these models train? So models learn through backpropagation. Backpropagation is basically how like a neural network is learning from its mistakes. So a prediction is being made and then it's being compared to the actual value. And the model is just calculating its losses and it just goes backwards and adjusts all of its weights to reduce its losses. I'm sure just like the previous two classes, the projects we did, it's doing the same thing. All the model is trying to do is trying to minimize the loss. So if we look at this like diagram here, it's starting with like an input layer. Yeah, and then it's like passing the input layer to be through these hidden layers, and then it's getting an output. And this output is being put through a loss function. So the loss is calculated, and then through backpropagation, the weights and like they're changed to make the loss like as small as it can be. Now going back to these like hidden layers, how do these layers affect the results? This is when we discuss like this is when like overfitting and underfitting comes into play. So underfitting occurs when the model is too simple, when the model is not like learning enough patterns from the training data. So in the code, this happens like if the model doesn't have enough layers or doesn't have enough neurons or not enough training data. Overfitting occurs when the model is too complex. The model is learning too much and it's just memorizing the training data instead of learning like general rules and patterns. So in the code, like this could happen if we're training the model for too long, or if it's too complex, if it has too many layers. Like you may be thinking like this doesn't necessarily sound like a bad thing, but one other way to look at it is like all the model is doing is just memorizing answers. It's not actually learning how to solve problems on its own. Like if you were to take a test and you're just memorizing like answers, if there's 20 questions and you just memorize 10 of the answers, sure you'll get at least 10 correct, but you're not going to know how to solve those other 10, so you're losing out on that. So when it comes to making like a good fit for our model, we wanted to learn the right patterns. We wanted to work well with both the training data and new data. Like all of the projects we've done, like all the projects you guys are going to do when it comes to building your own models, we want to find a model that works well with new and unseen data, not just the training data. And then lastly, so there are some different types of neural networks. This is not all of them, but two of like the main ones. I'm sure you guys have probably heard of CNNs, convolutional neural networks. They're mostly used for like images and videos. So they use these convolutional layers that slide small filters called kernels over images. And then at each position, they're multiplying the filter values by the input values and then finding the sum of that to create a feature map, which this is just showing like certain patterns and how they appear. I know it might not make a lot of sense at first. Like honestly, like when most people learn it at first, it doesn't make any sense. But next class, we're gonna go into a lot more detail and you guys will definitely get a better understanding. That's gonna like be our focus on our project next class too. Um, but the thing we're gonna be focusing on for our project today is MLPs, multi-layer perceptron. These are a lot simpler and general purpose networks. They're used for tasks like classification, regression, and pattern recognition. MLPs, they're made of fully connected and dense layers, meaning that each neuron is one, each neuron in one layer connects to every neuron in the next layer. This is like the type of model we're going to be using in our hand recognition project today. And then going into our project, actually is going to jump into that.
All right, yeah. So Azaveen, awesome. She explained it really well. We're going to be making a project today, and our project is going to be a handwritten digit recognition project. So if you've noticed in your phones, when you take a picture of something, sometimes it recognizes the text on that picture, or if you've noticed, in sometimes cars can read, like self-driving cars can read signs. All that is happening through AI. They're able to detect basically digits or letters and actually read them and associate them with text. So that is what we're going to be creating today, coding today, and we're super excited to make that. But before we get into that, I know we did throw a lot of information at you guys. So if you have any questions, now's the time to ask. Just leave them in the chat. We'll set some time aside to answer your questions. If you guys want to go back to a slide or anything, that's also okay. And adding to that, we're going to be exploring how everything that we just talked about applies to this project right now. So let's go into that. So we're going to be using this data set called MNIST, or Modified National Institute of Standards and Technology. So this data set is consisting of 70,000 images, which are sized by 28 by 28 pixels of handwritten digits from 0 to 9. So basically we have 70,000 images of numbers 0 to 9 in different handwriting, different fonts, and the sizes of each of these images are 28 by 28 pixels. Okay, so before we actually code, let's look at the layer architecture of the model we are about to make. And I see, Hannah, you're a little bit confused, and I'm sure many of you might also be. So I'll do a quick review of everything we've done as soon as I'm done discussing this. So then maybe if you're a little confused, I'll explain it really simply so everyone can understand. But if you have anything you're specifically confused about, leave it in the chat. So actually, let me just do that right now before I discuss this architecture, because if you guys don't understand what we discussed earlier, this is probably not going to make enough sense. Just to go super quickly through everything we've discussed. First, we started by discussing what neural networks are. So we started by discussing that neural networks are basically system of connected neurons that learn patterns from data to make decisions. Now, after this, we went into what neurons actually are. So neurons in AI and in math are inspired by something called biology, so our health. And in biology, neurons are something called cells. So brain cells, when anyone says the brain cells, they're referring to their neurons, basically. So in your brain, you have cells that are called neurons, and those neurons are responsible for responding to inputs. So let's say, again, going back to my hot stove example, when you touch a hot stove, your neurons will get sent signals that say this person is in pain or it's way too hot. And when those signals get sent to the neurons, they're processed, and then the neuron will react to that and it'll output a signal that tells your hand to pull away, right? Because when you're touching a hot stove, your hand is not going to sit on the stove and just let it burn, right? You're going to pull your hand away. But how does it know how to do that? It knows because your neurons are taking the inputs of pain and heat, maybe, and are processing it to output a signal, which is to pull your hand away, to other cells. So that's what neurons in biology are. Okay? So understanding that, in AI, neurons work the same exact way. So they take input, just like how our neurons in our brain took in signals. Artificial neurons, which are the neurons we use in our neural network, take in numerical input. So again, going back to this, we have all of our inputs represented by X. After that, these inputs are multiplied by weights, okay? So they're given different importances. So things with more weights, the neuron, the artificial neuron, is going to be more excited towards. It's going to look at that more than something that's less important or less weighed. Then the sum of all of these inputs after they've been weighed is calculated. Okay? We get the sum of everything. And then that sum is passed through an activation function, which Aveen already described as something that lets the neuron know whether to pass forward an input or not. Now, when you're coding it, you don't need to be coding individually what the weight is, what the transfer function is, all that. Like this is done behind the scenes. So everything that we've explained so far happens behind the scenes. So you're not making any of this happen. This is what is naturally happening in the neural network. Okay? So don't think that you need to be coding all this. So if you don't understand it fully, don't worry. This is what's happening under the hood. So you don't need to be making all this. We're just teaching you this so you know what's happening behind the neural network when you do make it. So having a general understanding, not if you don't get it exactly, is also perfectly okay and honestly enough. So activation functions, again, Aveen already discussed this. It's just letting you know if neurons should send a signal forward or not and how strongly. And these neurons can be arranged in networks, is what the point of this part was. So these neurons, which are each of these circles, can be arranged into layers. So each of these like columns of circles are a column of neurons, and that's called a layer. So the input layer is where inputs get inputted. Your hidden layers are, well, these inputs where the model learns these data, like these patterns from these inputs, and the output layer is basically where your prediction is made. So that's what these layers are. Yeah, the hidden layers are called hidden because you don't see the output, and they're the ones that do all the pattern finding and data calculation, and then the output is just your prediction, and the input are the inputs that you give to the model. So basically the point is these all these neurons, right? All these neurons, they do this function, and they can all be interconnected to make a neural network, which is what this image is showing you. It's just showing you that you can have multiple neurons that are fed into layers and layers and layers and more finely sifted for patterns, and then you can use that to make a prediction. And it'll make more sense when we code it. And then Aveen went over backpropagation, which is basically how models learn. So think of it, it's making its prediction. It checks, did I do it right or did I do it wrong? And based on that, it goes backwards and adjusts those weights to make it more accurate. That's all that backpropagation is. Nothing complicated. Overfitting versus underfitting was just a concept that told you guys how layers affect your results. So if you have too many layers, the model might not learn patterns, it might just start memorizing patterns. So it won't work well on new data. Underfitting happens when you have too little layers, so it's like learning less. It doesn't have enough time to get those patterns, so it doesn't detect those patterns as accurately as it should. And then Avina went over kinds of neural networks. So CNNs, don't worry about this. We're gonna have a whole class on it next class. But today we're working on MLPs or multi-layer perceptrons, which are basically that diagram we showed you earlier. All those neurons interconnected is an MLP. It's just telling you that the inputs are getting passed along a bunch of layers. That's all you gotta understand. Does that make a little bit more sense now? If it doesn't, you can ask us about specific parts you got lost in. Would be happy to answer. Okay, so I'm thinking that we don't have any questions, so we're good to move on. If you guys do have questions, feel free to ask though. So again, recapping, our project today is going to be handwritten digit recognition. So we're going to be talking about how we can recognize handwritten digits even if they're in different handwritings or if they look different. So that's what our project is going to be for today. Now, this is what our layers are going to look like. So I know looking at this, you're going to be like, what is going on? What are these numbers? Why are there so many lines? Right? Why is there 784 inputs? Well, to understand that, we have to first look at the fact that we're making an MLP or a multi-layer perceptron, which is that, where all those neurons were interconnected, where we made that network of those neurons. That's what we're making right here. So if you look into this, 784 is the number of total pixels in one image. So let's say we have an image of 9 here, right? You can see we have a 9 getting inputted. That 9 is sized 28 by 28 pixels. So this 9 is sized by 28 by 28 pixels, meaning that it has 784 total pixels in this image. Okay? Each one of those pixels is going to get inputted into our neural network. So you can see the first layer right here. Let me annotate to show you guys. This entire layer right here, this layer is our input layer. It's where we're putting our inputs. Now, each one of our inputs is going to be a pixel of our image. So that's why you see this number 784, because every image, or let's say, look here, right? This image 9. It's sized 28 by 28 pixels. So how many pixels are there total? Well, if you multiply 28 by 28, you get 784. So each one of those 784 pixels in that image is going to be fed into our neural network. So look right here. This is our input layer. So just think of that. I'm going to label that as I. That's our input layer. Um, Sorry guys, one second. We have a question. Does that make the 9 the input? Yeah, so the image of the number 9 is the input, okay? But every pixel of that image of the number 9 is the actual input that's getting fed. So the actual number 9 isn't the input. Every pixel of the image of number 9 is the input. So you see this image, right? Yeah. See, you see it's really pixelated, right? So every one of those tiny, tiny pixels is the input. Okay. So moving on, then you look at these layers right here. I'm going to label these as H for hidden layers, okay? And these hidden layers, the patterns, this model will pick up on little patterns from those little pixels in these hidden layers. So in these hidden layers, they're being multiplied by weights, they're being added, the bias is being added. Basically, the model is detecting the little patterns that are in these pixels. So you can see that every one of these pixels is being sent to a neuron in the second layer, which is our hidden layer. And within those layers, patterns are being identified by the model, and it's basically learning. So in these hidden layers, it learns. So you see every one of our inputs is connected to one neuron in the hidden layer. So that's what makes this a dense network. You see that see it's so like compact, you see a lot of lines. It's a dense network. So every one of our inputs is being mapped to one neuron in our hidden layer. You notice that? So we see all these neurons are interconnected. Just get that point. Every one of these neurons in the hidden layer is interconnected with our input. Okay, and then we see that those are being sent over to our next hidden layer. So the more hidden layers you have, the more patterns the neural network is going to identify. So that's what's going on right here. So we have neural hidden layer number one, maybe identifying, for example, maybe a curve, right? It's like looking, oh, so this 9 or the pixels of number 9 are making a curve. Okay. Number ones don't have that. Number sevens don't have curves, right? And then it's being sent to the next hidden layer, which might detect straight lines. So we see, okay, so there's a curve and also a straight line that looks like a number 9, just as an example. All you need to understand is that these hidden layers are picking up on really, really fine, fine, fine patterns within these tiny, tiny pixels. And through picking up on those patterns, they're learning. They're learning what these shapes look like. So that's what's happening in these hidden layers. It's basically like the mastermind of the entire neural network. Think of it that way. And you see that only certain neurons are being lit up within these hidden layers. Now, looking at that, you might get confused. Why isn't every neuron getting lit up? Well, then you think back to what Aveen talked about, which is our activation functions. So remember, activation functions decide whether or not that certain input is important and should be passed forward or not. So when these neurons you see are not lighting up like this one doesn't light up, right? Well, that's because that specific neuron applied the activation function on that input and decided that, hey, this is not going to help you make a prediction. This is like useless data, basically. Like this part of the image is not going to help you out. So let's say one pixel only has like a tiny square of black like this, right? You see this little square I'm drawing? Let's say that's 1 pixel. Looking at that, the model is not going to be able to tell what number that is, right? It's just a bunch of black pixels. The model is going to look at that and think there's nothing in here, right? The model is looking for our white pixels. So that neuron might decide to not fire, basically. It's going to decide to not send that input forward to prevent the model from getting confused. So you see only our certain important neurons right here are getting fired up. So looking at that, we go to our output layer, which is our final one right here. So looking at our output layer, you see a bunch of different values, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, those are all the possible numbers that our image might be. So as you can see, our image right here, number 9, gets mapped to this neuron right here, which finds that it is number 9. And basically, all you need to understand is that's like the final part of the neural network. It's going to basically get mapped to one of these neurons, which will tell you what the prediction is. I feel like it's pretty self-explanatory. If you guys still don't get it, drop a comment, let us know. But all you really need to understand is that this image is being broken into a bunch of pixels. Like watch it. See how it gets broken into a bunch of pixels? That one image is being broken into pixels, and each one of those pixels is being fed into our neural network. And after they're being fed into the network, these hidden layers that I labeled with H are learning the specific patterns within those pixels. So it's looking for specific patterns in those pixels, and through that, and through that, they're learning to make outputs. Okay, so Dia, I see that your internet glitched out. So you want me to explain what the hidden layers do again. Okay, so super simple explanation. Hidden layers, first of all, they're called hidden layers because you don't see the output of those layers. Okay? Those outputs of the hidden layers you never see. So first of all, that's why they're called hidden layers. Okay? Hidden layers, their function is to detect those patterns in our data. So hidden layers are basically where the learning of the model happens. In hidden layers, our inputs are multiplied by those weights and biases, and through that, sorry, there was a car going by. And through that, the hidden layers find the specific patterns in our inputs and basically keep learning from those patterns to detect what our output is going to be. So in this specific example, we have the number 9, right? And we have pixels of number 9 being fed into our neural network. So for example, a hidden layer might detect some curves. So it might say that, okay, so there's more white pixels that make a curve shape. That means it's probably going to be, let's say, an 8 or a 9 or some number with a curve. And then maybe our next hidden layer detects that, oh, there's also some straight lines. So it could be maybe a 9 because a 9 has a curve and a straight line. So that's kind of like an abstract example of what it might be doing. But all you have to understand is that our hidden layers are the ones that detect the patterns. It's basically the things that detect what will help us make the prediction, if that makes more sense. I
Yeah,
hope.
thank you. Yeah.
Okay, perfect. So this is basically what we're going to be coding. Now you might be looking at this and be like, oh my God, you expect me to make all that? Like that looks so complicated. But in truth, once again, I'm going to repeat this. This is what's happening under the hood. Okay? This is not what's happening, what you're going to be like physically writing out. Like all this will be happening behind the scenes, and once you code it, this will be happening in your computer. So our goal is to give you good understanding of what happens when you code and also what happens behind the scenes. And this is what's going to be happening. Basically, our image is going to be broken into pixels, which are going to be fed into our neural network. Hidden layers are going to detect patterns in our data. and then we're going to use that patterns to make an output, or basically tell us what number our image represents. So, having understood what we're going to be making, now it's time to actually go ahead and make it. So, um, Aveen's going to send out the notebook to go ahead and copy. So, let's wait for that notebook right there. Okay, so she sent it out. Please go ahead and click it. Let me clear my annotations. There we go. Please go ahead and click it. And if you've been here before, you know the drill. Make a copy by going to File and Save a Copy in Drive. If you don't do this, you will be thrown an error. So you don't want to be not doing this step. So again, you've known that you've done it right when your title says copy of student copy neural network solution with blanks. So make sure that you've made your copy. I'll give you guys like 20 seconds to go ahead and do that. All right, so hopefully everyone has made a copy of this blank notebook or this notebook with blanks. This is what we're going to be coding in today for our project. So let's start by a quick introduction, right? Today, we're going to be learning how computers recognize numbers, just like how we as humans can recognize numbers too. We're going to build a neural network that can look at handwritten digits and guess what number it is. So, this is like teaching a computer how to read these messy handwriting because not every number is going to be written the same way. So, why does this matter in the real world? Well, we already kind of touched on this, but your phone uses similar technology to read your handwriting or unlock with facial recognition. While it may not be looking at numbers, it may be looking at facial features on your face to go ahead and unlock your phone. It kind of works the same way. Or self-driving cars use CNNs to read road signs. So if you guys have heard of Waymo in San Francisco or even Tesla, they look at signs to see whether like a stop sign says stop. Once it sees that, it's going to know whether to stop or not. Like it reads these signs and processes it to create commands or execute certain commands like stop. Next, we have this picture, which kind of shows you what our data set is kind of looking like. So this is what we're going to be kind of giving to the model. These are not all the images. Obviously, if you remember, there's 70,000 images in the data set that we're going to be using today. But this is basically what some of the inputs look like. So the point is here you can see that not every number is written the same way. Like the number one here is written differently from the number one here. It's a little thicker. So we need to make sure our model can understand the difference, or rather understand that they're both the same number, even though they're written different ways. It needs to understand that this 7 with a line at the end is the same as this 7 with no lines at the end. Point is, we have to teach our model to be adaptive and learn to different handwriting. So, if everyone is ready, we're gonna jump into it. So, obviously, the different thing about this is we're not going to be actually needing to import certain files just because the data set that we're using, we can import it directly through code. So you'll see how to do that in just a moment. But let's get started with step one, which is importing the tools we're going to be needing for this project. So this is already done for you, just so you don't have to type everything out. But the point is, let's go over the libraries that we're bringing in for this project. So the first library is something called TensorFlow. TensorFlow is kind of like our scikit-learn. If you guys remember, scikit-learn helped us with models, is basically our scikit-learn for deep learning. So neural networks are not as simple as logistic regression or linear regression. So we need a bit more of a complicated library to go ahead and make our neural networks. So to do that, we import something called TensorFlow, which lets us build and train neural networks. So you can think of these as like little Lego blocks for AI. Like we can use Lego, like these little blocks, to build these layers and networks to go ahead and make predictions. So remember, we're importing TensorFlow as TF. So whenever we need to refer to TensorFlow, we can just say TF instead of having to type up the whole name. So that's what as TF means. Next, from TensorFlow.keras, we're importing layers and models. Now, what Keras is, it's an API or an application programming interface within TensorFlow. So it's basically its own set of commands and packages and libraries. So within that, from that like set of subset of commands, we're importing layers and models. Now, layers, if you remember, input layers, hidden layers, output layers, are what we're going to be using to build our model. And from models, we're going to be getting the kind of a neural network we want. Thirdly, we have import matplotlib.pyplot as PLT. This is just for plotting. This is for our graphs to show our data on a graph. PLT is just a short form version. We've imported this library before in our old code as well. Finally, we're importing NumPy as NP. Again, we know this library, we've seen it before. NumPy basically allows us to go ahead and do complex mathematical equations or help us do math with arrays, which are basically collections of data. So, understanding this, let's go ahead and jump right into loading in our data set. So the data set we're working with is called the MNIST data set. And again, as a recap, it has 70,000 pictures of handwritten digits. And the way we're going to be doing this is first you need to understand that this data set is already pre-split. So if you remember, in our old code, we had to do train test split, which means we take our data and we allocate a certain percentage for the model to learn from, and then we allocate a certain percentage for the model to test on. So the thing is, and for the MNIST dataset specifically, the splitting has already been done for us because this is a very popular dataset. So all we have to do is really create our variables that represent those split values. So we don't need to actually split anything, we just have to make the values that hold those splitted data. So in order to do this, we're going to do this line of code. So we're going to do x underscore train, y underscore train, in parentheses, comma, x underscore test, comma, y underscore test, also in parentheses, is equal to TensorFlow, or TF for short, dot keras dot datasets dot mnist dot load underscore data. Now I know it's a lot of dot, but that's really because we're just tagging on a lot of functions in one line of code. So looking at this line, let's see what it does. So we create four variables in this line of code: xtrain, ytrain, xtest, and ytest. And they functionally do the same thing as our old program. So xtrain and ytrain basically is the data that the model will learn its mistakes from. And xtest and ytest is basically the data that the model will test on and see how smart it is, basically. But what we're doing here is we're taking in our data with the load data function, pretty self-explanatory. It's just loading in the data from this MNIST package from TensorFlow. So it's already a predefined package, and all this function is doing is bringing it in and assigning variables to it. So that's just the convention for loading in the data for our project. And the next thing we're going to be doing is we're going to be looking at the specific data, like what does it look like? And in order to do this, we're going to explore the shape of the data, like what exactly does it look like? Is it a square? Is it a rectangle? What's inside? What do the pixels look like? So to do this, we're going to print something out. So go ahead and type out print. We're going to be printing out x underscore test dot shape. Now, what this does is it just checks the dimensions or how the testing data will look like, or just an example of what it will look like. So once you've typed print x underscore test dot shape, go ahead and run the code. Or actually make sure you run the previous cell. Make sure you run the import code cell, then the load MNIST dataset code cell, and then finally the x test dot shape cell to make sure you don't get errors. So if you're getting errors, make sure you're running every cell in order. So I'll give you guys a couple seconds to do that, and then we'll discuss what we just got as output. If you guys are getting errors, let us know. We'll try our best to help you guys out. All right, so I don't see any comments or anything in the chat, so that's my signal to move on. If you look at the output of x underscore test dot shape, you see it's 10,000, comma 28, comma 28. Now looking at these values, you're probably like, what does that do? Well, it's okay. I'll explain it to you. 10,000 is basically how much data is within this variable. Okay, so in x underscore test, there's 10,000 images. In just for testing, there's 10,000 images. Okay, that's what the first number represents. The next two numbers is basically the size of our image, or the size of the images within x underscore test. So you see it's 28 and 28, which means, as already discussed, each image is going to be 28 by 28 pixels big. So that's just how big it is. So 28 pixels by 28 pixels. Now we're going to do the same thing with the training data to see how that looks like. So we're going to do x underscore train dot shape instead of x underscore test dot shape. And we're going to see how the output differs. So go ahead and type this, print x underscore train dot shape. Again, what this line of code is doing is just finding the shape or the dimensions of the data within this variable. So go ahead, I'll give you like 5 seconds to type that up. All right, hopefully you guys typed that up. Go ahead and press the run button. And then you see another output, which is 60,000, 28, 28. Now, if the 10,000 in the previous print statement represented how many, if the previous, yeah, sorry, someone just joined. If the previous 10,000 represented how many images were in the x underscore test variable, what do you guys think the 60,000 number represents? Well, if you guys are thinking that that number represents how many images are in X underscore train, well, then you're absolutely correct. So 60,000 images are being used to train the model, or basically are given to the model to learn from. So adding up 60,000 and 10,000, you get 70,000, which happens to be the total number of pictures in our data set. So this is just showing you guys the split, okay? And then you see 28, 28, again, the same thing. It's just showing you that our model is gonna, the images in our model are gonna be 28 pixels by 28 pixels big. All right, so that is essentially what we did, and we just went ahead and explored what our data looks like. Now we're gonna go ahead and actually print out a piece of data, or basically plot out a piece of data to see exactly what's gonna be fed into the model. So in order to do this, we're going to be using our matplotlib library, which which helps us plot data. So the way we're going to do this is we're going to do plt, which again refers to matplotlib. We just made it a shorter name, dot imshow. Now, imshow stands for image show. So it's going to show one of our images in our data set. So plt.imshow x underscore train. Let's pick something from our training data set. And unfortunately, just writing this much isn't enough. We have to give it a specific image to show from this data set. So we do that by giving it something called an index. So in square brackets, you can give it any number. We're going to work with 13 just as a random number. But you have to give it an index, so it's gonna find the 13th image and show you that. So the index is basically which image you want to show. So make sure you give it an index. We're gonna give it 13 for now in square brackets. And just for, aesthetic purposes, for visualization purposes, we're going to give this thing a color, and we're going to do cmap, which is equal to color map is equal to plt.cm.binary. And to explain you guys what this code does, or this part of the code does, is it basically makes our image black and white. It makes it monochrome. So by doing binary, it means it's either going to be black or white. There's not going to be any other colors in our data. So that's what it's basically doing. It's plotting a black and white image. Now let's go ahead and run it. And wow, look at that. We have a number outputted through our plt.im show statement. So we have outputted the number 6. And looking at the 6, look at those pixels. Do you see those pixels? You can see each individual pixel of this um, image. Now, each one of these pixels is what's going to be fed into our neural network, and our neural network is actually going to learn the patterns in each one of these pixels. So I think this is really cool visualization of what's going to be fed into the model. If you guys want to experiment, you can change this 13 to any other number. Like let's say I do like 17 and I run it. You see I get another number. I get the number 8. So basically it's just pulling out different images from our data set. So I'll give you guys like 30 seconds if you want to go in and experiment with different numbers. So I'll do that too. Like I'm going to try 0. So it seems like our 0th or first element is a 5. Our second element is actually a 0. Point is you can go, all the way up to like random numbers and pick out different images to look at. And you'll see that each one of them looks different. So I'm going to go back to 13. And if you guys want to follow along with me, you guys can too. Now that we've visualized basically our data that we're going to feed in, let's go ahead and prepare it for our model. So to prepare it, we have to do a couple of things. So the first thing we're going to have to do is do something called reshaping. So reshaping and scaling. So we need to make all of our pixels into a similar format before we give it into the model. Basically, want to make all of these different pixels that look all very different, have the same formatting before we feed it into the model, just so that it doesn't get confused. Next, we want to scale these images to give them values between 0 and 1, so the model doesn't think that certain pixels are way more important than others initially. So what I mean by this is if you look up here, right? We have black pixels, gray pixels, white pixels. Now all of these have different values. Like if you were to convert these pixels into numbers, each one of them have different values. So the black will have a higher numerical value. That black pixel will have a higher numerical value than the white pixels. So that's just how it's made. There's not necessarily like a logic behind that or why it has a numerical value. That's just how it's made. So keeping that in mind, the values can be from 0 to 255. So you don't really need to know that. I'm just giving you guys some extra information. These if you were to convert these pixels into numbers, they can have a value ranging from 0 to 255, and that's kind of based on like their color and things like that. So 0 to 255 is a pretty big range. So all we're going to be doing is like normalizing it or like putting it all between a range of 0 to 1. So, it's all around a similar like range because we don't want like certain pixels to be more prioritized initially than others. So, keeping that in mind, let's go ahead and code that statement up. So, we're going to start by reshaping both our xtrain and xtest data sets. So, let's go ahead and start with xtrain. So, go ahead, xtrain is equal to, we're going to update the value of xtrain, x underscore train dot reshape. So reshape is basically rearranging our pixels to make it easier for our model to read. So within this reshape function, we're going to pass in a couple of values. First, we're going to pass in -1. Now, this -1 doesn't really have a meaning. It's just letting you know that you don't want to change the number of images in the data set. Like we don't want the reshaping to get rid of some images, right? We still want 60,000, say 60,000 images. So in order to uh, do that, we just say -1. It's just a convention. It's just how the function is hard-coded. So -1 basically tells the function you don't want to change how many images are in this variable. After that, we're going to do 28 by 28, we're basically feeding in the dimensions of our images. So we want this dimensions to be, reshapen and normalized. So it's all in a similar range. And finally, we're going to feed in the parameter 1, or rather the argument 1. And what this argument of 1 does is let this function know that there's only two colors in this, white and black. So 1 means that there's one color channel, which means that it's a grayscale image. So it's black and white, it's monochrome. If you were to do 3, let's say if I were to put in 3 instead of 1, it would be RGB, like a red, green, blue. Like then it would be a really colorful image. But since our data, as you can see, is black and white, we're going to do one color channel. So after this, unfortunately, our line is not done. We're going to give this a certain type, and we're going to do float 32. Now, I'll explain to you guys what this is in just a second. But after you type as type float 32, you want to divide it by the value 255.0. Now, go ahead, copy that down, and then I'll explain to you guys what this does. All right, hopefully everyone has copied it down. Let's go into what this does. So dot as type float 32 basically makes all of our images a similar format, basically. It makes everything a 32-bit float integer. So it makes basically all you gotta understand is that this function, dot as type, makes all of our pixels or all of our images in the same type so our model can understand them the same way. So this is basically just a format for our image to be put into. Next, we're dividing this entire equation by 255 in order to do our scaling. So remember how we talked about how these pixels can represent any number from 0 to 255 depending on, their color and their intensity. Well, in order to basically make them in a scale from 0 to 1, we divide by 255, just basic math, in order to make them all a similar scale. So let's say something is like 0, let's say something's value is 0. If you divide that by 255, it's still going to be 0. But if something is 255 and you divide it by 255, it's going to be 1. So that makes our max value 1 and our minimum value 0. And all values in between will be scaled appropriately. So this is basically, all you got to understand is this entire line is formatting our data in the similar way so our model doesn't get confused and doesn't think that there's different kinds of data. Now, all you gotta do now is just copy paste this line like this and change x underscore train to x underscore test because we want all of our inputs to be scaled and reshaped for the model because all of these are going to get input into the model. You don't want our model throwing fits and getting confused. So we're going to update both of our x values. So go ahead, it's just a simple copy paste and a change of the variable. We're just updating a different variable instead. I'll give you guys like 10 seconds. If you guys have questions, I'll also give you time to ask them now. All right, so I'm not seeing any questions, and I hope that was enough time for you guys to copy paste that line. Oh, okay, I see a chat. Oh, yes. Yes, thank you for noticing that, Ishan. I forgot that. Change also the X train in the second line of code to X test. Thank you for pointing that out. You are very right. Basically all we're doing is changing out the variable to a different one because we're updating the variable. Thank you for noticing that. So make sure you guys have done that. Make sure your second line only has X test in it and your first line only has X train. Give it a run to make sure that works. You won't get any output because it's not something you can necessarily output. Just make sure that works. All right. Moving on now, because I don't see any questions, we're gonna actually build our model now. So remember how we looked at that super cool architecture? I mean, if you want to look at it again, here's my slide. You see this architecture with input layers and these like hidden layers in between, and then our output layers. Well, this is where we actually define them and make them. This is honestly the fun part. This is where we're bringing our neural network to life. And actually, it's probably way easier than you think. So moving on, let's start by creating our model. So first of all, we have to instantiate our model or basically create an object. So, or kind of give our model a variable name. So in order to do that, we're going to do model is equal to models dot sequential. Now, what sequential is it's just something from our models library that tells the code that this neural network is going to have multiple different layers in a sequence. So it's not going to have like just one neuron, but the neurons are going to be arranged in layers in a sequence. So that's all that sequential does. So it basically groups a stack of our layers together, makes our model possible basically. So here we have created an object of our model, or basically the model itself, we've given it a variable name. Now we get to make our layers. So this is the fun part. So starting with our first layer, as you see in this GIF or GIF right here, we have to start with the input, right? And you see we have 784 pixels to input. So the way we're going to be doing that is we're going to do layers dot input, and we're going to do shape is equal to 28 by 28 by 1. Now, seems like I'm getting an error here. Let me go ahead and fix that. Um, One moment. Okay, just copy that for now. Hmm, I'll figure out why that's not working in just a second. It should work. Oh, thank you, Anvita. But that's not the error. Yes, but you do need to put 28 by 28. Okay, we'll get back to it in just a second. But this line will create an input layer, which will allow us to feed in our images of the shape 28 by 28. It's basically going to break it into different pixels, so 784 pixels, because 28 times 28 is 784. Yeah, 784. And we're going to feed each of those pixels into our code.
Sure, I think you just have to change it to the square bracket,
Oh,
right?
did I
Like
forget
after,
the square bracket?
yeah, I think so. I think that's still working.
Oh, okay. Thank you. Thank you. Okay. Yeah. Thank you. Let me just go ahead and change that over here too. Okay. Okay. So thank you, Amin, for pointing out my error. So the error was a syntax error, basically kind of like a grammatical error on my part. All you have to do to fix it is in your open parentheses after sequential, create a square bracket because we have to be feeding in arguments to this function. So that's why it wasn't working earlier because it was getting confused. So just go ahead and add a square bracket, and after layers dot input shape is equal to 28 28 1, go ahead and add an ending square bracket and ending parentheses. So we'll have to move this down eventually because we need to add more layers, obviously. But just do that for now so you don't get an error. So I know that was a little bit confusing, my bad. I'll give you guys like maybe 30 seconds to go ahead and get caught up in case you copied my error-filled code. So while you guys are doing that, just understand that this right here is creating our input layer. And all it is saying is expect images of size 28 by 28 with one channel. So they're going to be grayscale. So that means don't look for different colors. Don't worry about that. But expect images with 784 pixels, basically. Yeah, so basically inside layers input, we're passing in an argument that tells it what the shape of our image is going to be. So make sure you guys have that. And looking back, honestly, you see these last two, like this closed bracket and the closed parentheses. Go ahead and copy that and then move that all the way to the end of the code cell. So like down here after all of the comments. All right. Hopefully everyone has gotten caught up. Just a couple of things left. Next, we're gonna go ahead and create another layer that actually flattens our inputs. So the way you do this is to layers dot flatten. And what this does is it basically kind of squishes our 2D data, which has 28 by 28 pixels, into 1D data. So instead of having like 28 by 28, we're just going to get the number 784, which is a total number of pixels. So layers.flatten is basically just basically splitting our image into those individual pixels. So going back to show you the visualization of this, look at how this like image gets split. See how it like see when it got passed into input, you saw how it got split like that. That's exactly what's happening here from layers dots flatten. It's basically converting our 28 by 28 pixel image into a 1D vector of 784 numbers. So our 1D vector is basically a collection of data. It's just like kind of like an array. It's a little different though. It's math, it's kind of calc stuff, but just understand that this is basically ensuring that you get 100, 784 inputs instead of just 28 by 28. You're making 2D data into 1D data, so it's easier for the model to learn from and not get confused from. That's what layers.flatten is going ahead and doing. Now we have to make our actual layers that find patterns in our data. So now we're making our hidden layers. So the first hidden layer, or the way we're going to make our first hidden layer, is do layers dot dense, and we're going to feed it how many neurons we want in our layer. So we're going to do 128, and we're going to do activation is equal to ReLU. Now, I hope you guys recognize some keywords in this line. You see activation, and you saw me mention neurons. Now, this 128 is how many neurons are going to be in that layer. So going back to our visualization here, you see that there's a bunch of neurons. So how many neurons are going to be in our hidden layer? There's going to be 128 neurons. So that's just what it's specifying. Okay, and then our activation argument here is specifying which function we want to use. So recall there's many different kinds of activation functions that decide basically what inputs are important and what inputs are not important, and basically how important they are.
They are.
They basically determine if they get sent forward or not. So we have different activation functions, and in this case, we're using ReLU, which is the function that basically makes sure that you have no negative numbers. It's the one where everything on the left of the x-axis is just a straight line, so it's just 0, and then everything to the right of the x-axis is an upward line, so that is going to be our positive values. So again, what ReLU or this activation function is doing is it's just deciding whether the inputs are important or not and whether they should keep going forward to continue influencing our model's prediction. All right. And one more thing, if you're looking at dot dense and are wondering, well, why does dot dense make a layer? Well, the answer to that question is that dense basically means that every neuron in this layer is connected with every neuron of the previous layer. So because we're making that kind of model, we use dot dense. There are different kinds of models though. So just because all of our neurons are interconnected, we use the word dense because think of it, when everything is connected together, it kind of packs everything tightly together, and that makes everything more dense. So here we've created our first hidden layer with 128 neurons and the activation function ReLU that basically helps us learn complex patterns by deciding which inputs go forward and which ones don't. Now, unfortunately, one hidden layer is not enough, right? We have many different numbers with many different handwritings, and we need to now get other patterns in the data, right? We can't just do one layer, find one pattern, and expect it to get the answer right. There's many patterns in numbers, right? Curves, lines. Simply one layer is not sufficient enough to do that. So we're gonna make our second layer, And we're going to do layers dot dense, similar convention. This time we're going to do 64 neurons, and our activation is still going to be ReLU. So the reason we decreased the number of neurons is because, remember, some neurons will not pass forward the information because the activation function will determine that, this input is useless. It shouldn't be influencing the model's prediction. So we don't really need as many neurons to keep moving forward. So if you look back at our diagram, in this case, the neurons stay the same, but we don't need it to stay the same. We can kind of like crack down on the number of neurons in our layers, make it a bit more selective, if that makes sense. So it basically makes the model a bit more picky. Our activation is still going to be ReLU. Again, we're doing the same thing. We're basically giving the model one more chance to learn more patterns from the data. That's what making the second hidden layer is doing. Now, if you guys When we reduce the number of neurons, is there a specific number we need to decrease them by, or is it random? Great question, Bhargavi. And typically, you find this out through testing. So there is no specific number that you need to be, decreasing by. The way you get numbers is by testing. So first, you try with certain neurons, then you look at the prediction and you see, can I make it more accurate? Does it need to be less accurate? And based on that, you can address the neuron count. Maybe if you need to make it more accurate, you can increase the neuron count. If it's basically, remember the underfitting, overfitting concept we went over? Like it's memorizing things, or it's not learning enough. Everything, all the values from the number of layers, from the number of neurons, so the activation function, you can get that just through testing. Like there is no set convention to go in and find how much you need. You just test, see how your data or your prediction changes, and based on that, you can adjust for layer counts or neuron counts. So yeah, I was just about to mention, you guys are probably might also be wondering, how do you know you only need 2 layers and maybe not 3 or only 1? Well, the answer is you don't know that. You find out through testing. So you start with 1 layer, you test, you see that, the accuracy is kind of low. Maybe we need to add another layer to boost the accuracy so it gets one more chance to learn or one more chance to identify new patterns. So you create another layer and you just keep doing that until you get a good accuracy that you're satisfied with. And you do the same thing with neurons. I just divided it by 2 just for like ease of understanding. But yeah, I hope that answers your question. So now we've created these 2 layers that will find patterns within our data. But now we have to create our final layer, which is this one right here, our output layer. So in order to go ahead and make that, we're going to do the same thing. We're going to do layers dot dense 10 activation is equal to soft max. So let me just type this out and then I'll explain to you guys what this line of code is doing. All right. There we go. So go ahead and type that up. I'll give you guys a second. Okay, so what this last line of code is doing is it's making another layer with 10 neurons. And what major thing that's different here is that our activation function is now different. So our activation function we're using now is softmax. And Aveen talked about this on her side, but what softmax basically does is it outputs basically a probability, or like it just kind of gives you the class that your image is going to be falling under. So softmax will return a value from 0 to 1, and it just gives you a probability of a certain class. So through that probability, we can see what class that um, our specific image is going to fall into. So let me go ahead and make sure all this is right. Make sure you guys add commas after your lines of code, like after our hidden layers, go ahead and add commas. I realized I forgot that. That will throw you guys an error if you forget that. But point is, after when you make your hidden layers like these, first hidden layer and second hidden layer, put commas after, so the function knows that these are all like arguments being passed into it, and it's not like just one giant line of code. The last line does not need a comma because it's the last argument of the function. So within this entire code cell, you guys have just made this architecture. Can you guys believe it? With what you've done through these simple, 4, 5, 6 lines of code, is you've made this complex architecture that the model is actually going to be going through. So you've made it our input layer, which goes in and takes in our image. You've made a flattened layer that goes ahead and breaks everything into um Bhavana, you asked if the equal sign between the activation and the ReLU have to have a space. Here it doesn't matter. You can have a space or it doesn't matter. Like it doesn't matter. It's just a style thing. If you want to make it look a little nicer, look a little bit more spaced out, you can add a space. If you don't care, you don't need a space. Yeah. Back to what I was saying, we've created a flattened layer that just goes ahead and breaks it into our 784 pixels that you see right here. Watch our image. See it gets broken down. Then we've introduced two hidden layers that are responsible for finding the patterns in our data through activation functions. And we've given them neuron counts, which remember what neurons are. They're basically the basically they're modeled after our brain neurons. They take in inputs, they calculate the total sum of the weights, and then they pass it through our activation functions. And through this, our model has hopefully, fingers crossed, learned the patterns within the MNIST dataset to identify different numbers in handwriting. So before we go and test it out, there's still a couple steps left. And for those steps, I'm going to be throwing it over to Avid, who will teach you guys the rest of the code.
Okay, perfect. So now that you guys have actually built your like neural network, the next step that we're going to do is compiling this model. So we're going to be using the dot compile method, which basically just prepares the network for learning and it like sets up how it's going to measure its performance. So in the dot compile method, we have three different parameters. The first one, so it's like a loss function, which through this, it basically just we're deciding how it's going to measure the mistakes. And we also have an optimizer, which we're choosing how it's going to update its knowledge. And then we're also going to decide what metric we're looking at, which is basically like what we're going to be tracking during the training. For ours, we're going to be looking at accuracy. So in the actual line of code, that's like model.compile, and then in parentheses, optimizer is equal to Atom, comma, loss is equal to sparse categorical cross entropy, comma, metrics is equal to accuracy. And just like while like we're putting the code up there, while you guys are copying that, just to break down what each of these things are. So optimizer is equal to Atom. Atom is basically like a popular algorithm that adjusts the model's weights to reduce errors. You could think of it like a smart teacher that's like helping the model learn faster and better. Loss is equal to sparse categorical cross entropy. You guys may have heard categorical cross entropy before. Basically, this is measuring how far the model's predictions are from the true labels. The sparse version, we're just using it because our labels are just integers from like 0 to 9. Like when we're looking at the images, that's the label. We're just deciding what number it is, so that's why we're just using the sparse one. And then metrics is basically what we're going to be tracking. And for our specific thing, we're tracking the accuracy, which is like how often the model's predictions are matching the true labels. Or is the error we're getting? Okay, yeah. I'll give you guys a second to like copy that down, and then once you have that, you can like run your cell. We're not gonna get any like output for this cell specifically, but this is all happening like behind the scenes. Just it's like preparing the model to learn. Yeah, so in our next step, we're gonna be actually training the model. So this is when the model is actually gonna be learning from the images. So for this code, it's just we're creating a variable, it could be history is equal to model.fit, and then in parentheses, xtrain and ytrain, comma, epoch is equal to 5, comma, batch size is equal to 64, and then comma, validation split is equal to 0.1. So if you guys remember previously, like Devshri explained, when we like created the variables for separating the data set, we have xtrain and ytrain, which for here, the xtrain and ytrain is like our input images and their correct labels, because it's like the training data. And the model is looking at these to figure out the patterns. Epoch is equal to 5 means the model is going to go through the entire training set 5 times. It's going to be learning a little more each time. Batch size equal to 64. It just means that the model is looking at 64 images at a time before updating its knowledge. It's just helping it learn more efficiently. And then lastly, validation underscore split is equal to 0.1. It's basically just setting aside 10% of the training data to check how well the model is learning on like data it hasn't seen yet. Um, we're getting another error again, but if you guys are like either you're following along with the code or if you're just watching it and you're gonna go back later, just if there's any like syntax errors you guys are catching too, just let us know.
Yeah, and this kind of reflects the entire process of debugging. You're gonna get errors when you're making your code. The thing is, how do you go about solving them, right? Typically they can be syntax errors, like probably it's a syntax error right now, misspelling. You can always look down here to see what kind of error it is, but that's always a challenge with coding. You're gonna get bugs and you're gonna have to debug it. So give me like a couple
Mhm.
of seconds to figure out what's going on here. I think it's probably like a syntax error. But yeah, I mean, you can like maybe.
I'll just continue on from like that thing. Basically, like in this thing too, we're using the dot fit method, and what it's doing, it's just returning like a history object. It's like just collecting like all of this like data that it's collecting data while the notebook is running through it. And basically, it's just keeping track of like the training. It's keeping track of four different things. The first two things is training loss and training accuracy, which is telling us how well the model is doing on the data that it's currently learning from. It's also keeping track of validation loss and accuracy, which is telling us how well the model is doing on like a separate like check set of like the data it hasn't seen before.
All right, I found the error. It was just again a spelling mistake, missing an R. So everything should work just fine. Oh, well, we got one person. Let me take a look at this. Okay, we can finish the code and then we'll go back to this error.
Yeah. Um, So yeah, all this is basically doing, it's just like, it's basically just telling the computer, it's just practicing a skill. So the model is looking at examples, it's making guesses, and then it's checking how close it was, and then based on that, it's improving over time. Oh, Ishan is saying that his code is working.
Yeah, I think it's gonna be like a spelling mistake or something because the logic is all there. So, I mean, I can double check it one more time. But if we don't find it within like a minute or two, we'll move on, and then at the end of class, we'll come back to it, okay? And the solutions will be posted so we can always compare against that. I mean, let me know if you catch anything.
Yeah, I'm looking too.
I found the right here. Yep. Thank
Oh, okay, thank you so
you.
much.
Yeah, so like Dia, check if categorical is spelled right. Honestly, these are all just like tiny, tiny errors, typing and things like that. We are going at a fast pace, but like yeah, just check. It's often, most often a syntax error because the logic of this code is right. Okay, yeah.
Now hopefully it's gonna run.
Yeah, so take a look. When you train your model, you will be able to see this output. Aveen can explain what this output is doing.
Yeah, so just like if we look back at the code, we assign epochs as equal to 5. So that's why it's going through the data set. It's looking at what it's trained. It's going through it 5 times. And then if we look at the numbers here, the first two we can see is accuracy is equal to like at the end, it's equal to 0.9854, and then loss is equal to 0.0459. So this is basically just like the training loss in accuracy. And then next to that, we have the validation loss in accuracy. And it's pretty cool because each time that it's going through each epoch, you can see how the accuracy is increasing and the loss is decreasing for each of them, which is showing that like your model each time, it's like improving over time. Yeah, hopefully you guys got a chance to run that. And yeah. And so now that we have like trained our model, we can actually evaluate it to see how well it's going to work on new data that it's never seen before. So for this code, we could just create two more variables, test underscore loss, comma test accuracy is equal to model dot evaluate, and then in parentheses x test, y test is equal to verbose, comma verbose is equal to 2. So we're just referring back to those like other two variables that we got earlier when we were splitting the data. These ones is X test and Y test. So it's like unlike the previous code. Now we're looking at the testing images and their correct labels. This is what the model is using to check its predictions. And verbose is equal to 2. It's just showing like a progress log so we can see what's happening. And when we run it, model.evaluate, what it's giving us, it's just giving us like, so test underscore loss, this one value is showing us how far off the model's predictions are from the testing data. Oh, sorry, how far the model's predictions are on the test data. And then test accuracy is showing us how often the model predicted the correct digit. And just to like get like the actual output we could see too, we could just have a print statement, like print f string test accuracy colon test accuracy. Or yeah, we could just do it like that just to make it easier. So now we can have like an actual output and a number that we can understand. Yeah, so we can see here it's like 0.972, which is pretty good. It means like we basically got an accuracy of 90. So the model basically checked like 97.2 of the test digits correctly, which is pretty good.
You guys want something that's closer to 1. So if the test accuracy is like lower than like I'd say 0.8 maybe, you should go back and retune your model. So that may mean
Mm-hmm.
adding more layers. That may even mean getting rid of some layers because again, they're overfitting and underfitting. Those are both really important parts of machine learning, and Aveen discussed those concepts earlier. But just you need to note that when you look at your accuracy, it's not always going to be as accurate as this. Okay? When you have accuracy that's low, it's your job to go back to look at that architecture that we made with the layers and tweak it to get the accuracy that you want. So maybe something is way too like let's say it's like 0.5 and you want to make it a bit more accurate, you might add one more layer to find more patterns in the data. Or you might add more epochs, which is how many times, it goes through the model to learn. You might increase that a bit. You might add more neurons. You might think you need more data. So there's a lot of factors that go into like hyperparameter tuning, that's what it's called. But just know that looking at the error like this, you should be able to respond accurately, like if you get a low one. But in this case, we have a high one, so we don't have to worry about that.
Yeah, exactly like Darsha was saying. I think someone asked earlier too when she was like creating the actual model. They're asking about like if the numbers are like random for like the neurons and stuff. But like this, like when you're looking back here and you're actually like evaluating the data, this is just like Darsha was saying. This is when you would go back and you would adjust those values. You would adjust how many layers you have or how many neurons are in each layer, so you can get the highest amount of accuracy possible.
Yeah, and it's all just like playing around with it. Like
Mm-hmm.
there is no like specific formula that you need to use to get a certain output. Like you have to go change one thing, run everything again, see how it changed. Did it help? Did it not? Just try and exhaust your options until you get a good accuracy, basically.
Yeah, and now that we have like trained our model, we have like a 97% accuracy, we can actually make a prediction with this trained model. So first we're just gonna like pick a single test image. So we can create a variable sample is equal to X test, and then we're gonna be doing the same thing earlier. If you guys remember, we were looking at the data set and we use like the index. So we just do X test and then in those square brackets, like we could do 13. And then we're gonna use the dot reshape method, reshape and in those parentheses 1, comma 28, comma 28, comma 1. And what the reshape is doing, it's basically just letting the model know that it's one image with like the correct dimensions, like from earlier, the 28 by 28 pixels. And then in our next line of, so this is like, this is the single test image. And then our next line of code, we could actually create the predictions. We could create a variable like prediction is equal to np.argmax, and then in parentheses, model.predict in parentheses sample, and just close parentheses. So the model.predict and then with the parameter sample, it's just giving us the probabilities for each of the digits, 0 through 9. So it's looking at the image. So we have the single image here, which is sample. And then using the model.predict function, it's just telling us what the probability is that this image looks like 0. What's the probability that it looks like 1? And then using the np.argmax function, it's picking the digit with the highest probability. That's what the model's guess is going to be. So if it's like using like do the model.predict function, if it's predicting like 90%, it could be like number like 0 or something, then that's what the np.argmax is going to choose as the model's guess. And then finally, just to get like an output, we can print out both the predicted digit and the actual digit so we can see if the model got it right. We could just do print and then like in parentheses, just like a heading like, yeah, predicted digit, and then just print out the actual digit, which would be y test. We're just referring back to that index, y test, and then index 13. Yeah, so if we run it, we see that our model predicted it correctly because the predicted digit is 0, and then the actual digit is also 0. And then if you guys are copying down this code too, and if you want to play with it too, you can also adjust these indexes. So let's say we do something like 20, then we would get, so it's basically going to refer to, I think it's going to be the 21st image in the testing set because Python starts counting with 0. And so yeah, we're getting the same thing again. We're getting predicted digit is 9 and actual digit is also 9.
That shows how accurate our model is because you see every time we're going, right? Every time we're changing the index values of these, we're getting the prediction right.
Yeah, we're basically just asking, we're showing the computer model this image, and we're asking what number do you think it is? And we can see here that's predicting it accurately. And now that we have that, if we want to like, we have a question. How does the model know to choose a number? So that's through, so what it's basically doing through like the model.predict sample, it's like going through these like, it's going through each of the different possibilities that it could be. And then based on those probabilities, the np.argmax is choosing the highest probability of which number that it's most likely to be. And then that's what it's going to output.
Yeah, and also like scrolling back up, right? Like, let me show you something. Did we input the possible number earlier? No, we inputted a number in a handwriting that the neural network had not recognized yet. So again, this data set is made out of different numbers, which are images, by the way. They're not text. So I think you might be thinking that we're like literally putting the number 6 in like a numerical digit, but no, it's an image. So it's taking the image and classifying it into the text version basically. So that's what it's doing. And did we input the possible number earlier? We inputted an image. So we gave it an image with the number in it. So does it just really all the model got was an image, okay? And what the model did was it looked at the image, it analyzed the shapes in the image, and then it mapped those shapes to a certain number. So that's how it works. It doesn't take in the actual number. Like we don't say we're giving you the number 7. Okay, that makes sense. Perfect.
Okay, now in our last step, all we're gonna do is basically just display the image that we made the prediction on so we can actually see it. Like we printed it out that the predicted image is 0 and the actual digit is 0. But if we want to see like the actual image that we were looking at, basically we would just do using the matplot like function library, we would just do plt dot imshow and then in parentheses whatever like index we were referring to. If we want to go back to like either 13 or 20 or yeah, that was the original one, so if we just change oh yeah, it's 13. And then dot reshape 28, comma 28, comma CMAP is equal to gray. So we're just reshaping the image back to 28 by 28 pixels so it looks like the original digit. Because if you guys remember originally, we like flattened the image, but now we're just turning it back so we can see it better. And then the CMP is equal to gray. It's just showing the image in grayscale, black and white. If you guys remember too, we were looking at, I think it was the binary, which is also making it on black and white. We're just doing the same thing, making it grayscale. And our next line would just be plt.title, and then in parentheses, like prediction. This is just like putting the model's predicted if digit like above the image so we can like see if it's like accurate or not. So like there's the image and then on top of it, it's just gonna tell us what it predicted. And then lastly, the last line of code is just plt.show, which is actually gonna display the image on the notebook.
I'm just gonna print out the prediction as a title, so it'll just tell you the number.
Oh yeah, so now if we run this, we can see here that we see the digit, the actual image, we have a 0. And then also if you look at the title, when it's printing out the prediction, we also have a 0. So we can see like with our eyes, like visually, we can see that it also predicted it accurately.
Yeah.
Yeah, so you guys have just made your own like hand prediction. It's really cool. Neural network.
Yeah, and the cool thing is that this image, like Aveen said, this image is what we gave to the model. And this text at the top, the 0, is what the model gave to us. So you can tell that clearly the model is succeeding in taking images and converting them to text. Yours is predicting 9 for everything. Really? Wait, I've never. Did you change the index? Are you changing the index of the right things? Yeah, okay, wait. Are you changing the index of X test and Y test?
You know, actually, I was messing around with it earlier too, and I think in the actual like testing data, I don't know how it separated it, but a lot of the numbers are actually similar. Like for me, when I was doing it earlier, I kept getting a 0 a lot. So sometimes it just like depends on what index you're using. You have to just like choose like a random one and it might give you a different number.
Hmm. Okay, that makes sense, yeah. Yeah, try that. Okay, cool. So that's really awesome. We just made our own neural network project. We made this whole architecture basically in those couple lines of code. And we see that our model succeeded because the image that we fed into the model and the image that got outputted and the number that got outputted was match. See, it matches up. So it got this and it came out with a 0. Ishan, another good way is that if your plot at the end is like accurate, like if the image and the predicted like the title are matching up, then your model is just working, and that means that, it's just a flaw with how the data is split. Yeah. Okay. All right. So having said that, we're gonna get into our announcements and some exciting officer or like team role, officer leadership opportunities for you guys. We will be sending applications out for these soon. So let's go. Okay. Moving into this. Okay. Aveen, do you want to do it?
Yeah, sure. So, our final class is going to be next Saturday, September 27th, same time from 8 a.m. to 10 a.m. PST. Next class, if you guys, we kind of touched on it today, but we're going to be covering convolutional neural networks. We're going to go into a lot more detail, and you guys, I'm sure you guys are going to get a better understanding of that. And we're also going to be doing our final research project on breast cancer detection. So hopefully you guys are really excited for that. And like always, these slides, the notebook, the recording of the class, and the assignment are all going to be posted on Google Classroom later on for you guys to look back at any time. And yeah, make sure you guys are just always checking your email and Google Classroom to stay updated. Be sure to follow our Instagram and TikTok at YouthXAI. And as always, don't be afraid to ask us any questions. If you guys are confused about any of the code or anything like any of the concepts about neural networks, I know it's like a pretty complex topic, but it's really interesting too. And it's like a fundamental of a lot of like AI projects. So if you guys have any questions, let us know. And then for the most exciting part is our team applications. We are going to be offering some different positions. So we have a social media manager, which is going to basically like, we want you guys to just help us come up with bigger picture ideas for our Instagram and our other platforms, like reaching out to other nonprofits and accounts or partners just to help our page grow. And we really just want ways to like connect with more people. And aside from that, we also have a content creating position where you would basically like actually post regularly, regular content for like our Instagram and our TikTok, like basically like using your creativity just to create posts that are engaging, creative, and connecting with our audience. We also have a journal writer position, which I think we discussed that another class, we touched on it. Basically, you're just going to be like sharing stories, research, or creative writing on any like topics about like AI or any technology, like innovation, anything that that will inspire our community. And basically, you're also going to be gaining experience in publishing and contributing to our blog slash journal. And one of our bigger positions as well is a chapter founder. Basically, you would be like starting and leading a local chapter in your area, like at your school or just in your community. It's just like a branch of YouthXAI where you would just recruit members and organize events. It's basically to like help spread our mission and help us grow. We would provide you with all the resources necessary and all the guidance so you guys it would be really easy for you guys and it would just be a really great opportunity for you to build leadership skills and make an impact on a larger scale. And as well, like not only through any of these positions, if you guys are interested in applying, you're going to be gaining valuable experience. You're also going to be helping us spread our mission about spreading like education about AI, and all of your contributions are going to be counting towards volunteer hours. So you would be able to make an impact and gain volunteer hours.
Yeah, and on top of that, I'd like to add if you do apply for chapter founder in your community, you can call yourself the founder and president of a Youth XAI chapter. And I think founder and president of anything of a nonprofit or a branch or anything is a really big deal. So if you guys are interested, I highly encourage you to apply. Given also remember that we're going to be providing you with all the materials you need to lead a successful chapter in your community and create more impact. So while you'll be able to call yourself founder and president, and you will be responsible for assembling your team, we'll provide you with all materials and everything necessary to get kickstarted and make an actual impact in your community. So it's kind of like a Kickstarter for you to actually start getting involved in your community. I was also probably thinking, I mean, we could even potentially add a curriculum development role. So if you guys are also interested in helping us make curriculum for clubs, for classes like this, more AI related curriculum, if you're interested in applying your skills there, in researching topics and then making slideshows about it and helping us teach it, we'd probably also be open to that. I mean, we haven't fully established that yet, but we'll send out our final forms today. So please apply. We highly encourage you to apply. This is a great opportunity that not many people get. We've made these opportunities only exclusive to our students as of now. So you guys get first choice as to what positions you guys want to fill. Any of these positions are great. Keep in mind though, yeah, keep in mind the incentives. You get leadership. You get to call yourself really great titles. You get to show your involvement not only in your community but also with technology. When you do things with technology beyond just making projects and projects, it shows that you're actually serious about it. Because many people they just keep making projects and then they think they're involved. But the thing is, if you're actually spreading your knowledge, not only does it look really good on your part, that you're taking the initiative to learn, but also teach others. But it also shows that you're genuinely passionate about technology and it shows that you actually care. When you do all these extra things over just, making some AI code, it shows that you care. Okay? And people love to see that. College, just in general, even beyond college, admissions officers, they all love to see involvement in your community. So if you're lacking that, or if you're interested in just getting into it in a super easy, fun way, I'm sure I'd love to interact with every one of you guys. Just apply. It doesn't hurt, it doesn't cost anything. Give it a shot. Um, we'd love to read your guys' applications of these awesome roles, maybe even more. And yeah, we really appreciate you guys for joining today's class. I hope you guys learned something. And yeah, thank you guys so much for
Yeah,
coming.
thank you guys. We'll see you guys next week.
Stay tuned for our applications. Bye bye.